taught a course for 2 years, so not many of the students would know me. My name is Matthew Jacob. I've been a professor here since 1991, January. So I'm one of the senior faculty of the department. And today I'll talk about quantitative evaluation techniques in computer architecture. Right now, all of you know that computer architecture is in some way related to the design of the components of computers and how they interact and how they can be put together. And therefore, in any design activity, evaluation is an important co-activity because the designs have to be evaluated and potentially improved. So in computer architecture, there's a wide variety of different requirements for doing evaluation, and they typically require special purpose kinds of solutions. So it's not like you can always use simulation to solve all your problems in computer architecture, right? Okay. Now, just to get the talk started, let me give you a few examples of evaluation objectives which might arise in computer architecture. So this is one which frequently arises. Somebody has a design idea, a design change idea. So there's an existing design, they have an idea about how they can improve it, and they want to compare the old design and the new design quantitatively. They want to quantify the improvement. Another, which is a little bit rarer, what is the best system configuration for this particular program running on this particular input? This is an odd evaluation objective, but you'll realize that this might actually be an important one because of situations like embedded systems. Think about the computer system, microcontroller, what it is inside your washing machine. I'm sorry, inside the washing machine in your hostel. Right? That runs a one or two very special purpose applications. It doesn't run a lot of different applications. And therefore, the design of that could probably be optimized for a particular program running on a particular input. Right? So this is not, in fact, a lot of the work which I'll talk about is actually applied in embedded scenarios, not in general purpose scenarios. Okay, let's start by just considering the performance of a computer. Because in comparing two alternatives, you might be worried about which performs better. This is one possibility. You could be worried about other things, like the amount of energy required for one as opposed to the other, or the volume of one as opposed to the volume of the other, and so on. We'll concentrate on performance in this talk. Right? So the issue then is, how does one evaluate the performance of a processor? Now, one thought which might come to mind is you could use a metric which is independent of the program, a program independent metric. And these are not often useful. An example is the peak gigaflops measure, right? You could compute the peak gigaflops of a processor by figuring out how frequently floating point gigaflops stands for billions of floating point operations per second. And you could calculate the peak by just figuring out how frequently you can initiate a floating point operation and how long each floating point operation takes. And therefore, this is only of theoretical interest, because you'll rarely find programs, even in toasters or washing machines, which will have a requirement of the peak gigaflops. Another way of thinking about this is, all of you think in terms of, well, MTech students think in terms of CGPA. You could also think in terms of peak CGPA. What is the peak CGPA? In your first semester, your peak CGPA is, what's the maximum possible CGPA that you could achieve? It would be 10. After one semester, your peak CGPA will come down, because in some cases, the peak CGPA will come down. But again, that's not often a useful metric for a student to have in mind, because that is looking forward with a particular number in mind. So even in this world, program independent metrics are not often very useful. So I won't talk about any of those. Now, if everything is program specific, all the evaluation that we're going to do, then the choice of programs becomes very important. You can't just use any programs. And in fact, it would be nice if we understand how the program processor performance on the program depends on different aspects of the program. So very clearly, it depends on what the program does. In other words, the source code of the program. But it also depends on how the source code is compiled. You could compile it with very non-optimal optimization flags, and then the resulting program might have worse performance than a more optimized program. It also depends on what input is used. For any given program, you might be able to find an input on which your program runs extremely well. Right. So the bottom line is, in the world of computer architecture evaluation, it becomes necessary to have some kind of normalization so that everybody is talking in terms of the same evaluation settings, which is why there's an organization called SPEC, System Performance Evaluation Corporation, which is a non-profit organization which basically is in the job of generating benchmarks, benchmark programs, make files, and input files, so that the entire problem is solved. People will use a particular spec program on a particular spec input, and that will have the same meaning to anyone anywhere in the world. Right? So the problem of choice of program and choice of input will go away. I'll talk only in terms of the spec programs. Again, in some settings, like the washing machine, the spec programs are not exactly relevant, but we'll restrict ourselves to this in the examples that I use. Okay, so what are the options? How can you do evaluation? I'll just give you a slate of the options I'm going to talk about. The first thing is you could evaluate performance by measuring it. So if you have access to the computer, you can use measurement. If you don't have access to the computer, then you have to use modeling. So if you're in the job of designing, then the thing which you're going to design does not exist. Therefore, obviously, you cannot use measurement. Making measurements on a prototype might not be realistic because the actual implementation might not have performance. There might not be a tight correlation between the performance of the two, even though functionally the prototype might be identical to the end product. Right? So you may have to do modeling. Now, in the case of measurement, I'll talk about measurement towards the end briefly. I won't talk a lot about measurement. I'll just use one measurement example. So to do measurement of performance, you need some kind of hardware or software probes. But today that's not too complicated because all processors have some kind of hardware performance counters, and by picking the right events, by counting the right things, you'll be able to get some way to estimate performance, right? Whatever measure of performance you're looking for. Now, as far as modeling goes, I'm going to talk about three different approaches to modeling. One is analytical modeling, which you all would have heard about in various other courses. The other is simulation. How many of you have never heard about doing simulation for studying a system? Okay. And finally, you could do things empirically. Right? And what I mean by empirical is that the model is built based on observations or measurements, experiments done on a system. Empirical models are built out of empirical data. Okay, I'll talk about all three of these a little bit. Now, in the realm of computer architecture, the least frequently used of these three modeling options, is the analytical modeling. Right? But I'll talk about one example. In all these cases, when I talk about an example, I'm going to give you a quick overview of the intent and a quick overview about what it does. Right? And I'll cite the source papers, and you can look at them. Okay. Now, there are very few computer architecture papers which actually talk about analytical modeling of processors. And one of the first and one of the easiest to read, and which is still somewhat realistic, and which is going to, the ideas of which are going to recur as I go through the talk, is by Karkanis and Smith from the IISc 2004. IISc is one of the top computer architecture conferences. And it's trying to build an analytical model for superscalar processor performance. Right? So the intent of this paper is to model and estimate superscalar processor performance for a particular program and on a particular input. Right, now the measure of performance that it's seeking to estimate is CPI, cycles per instruction. So across the whole execution of the program, you count the total number of processor cycles that it takes and divide that by the total number of instructions executed. But we'll think about this. Today it makes more sense to think about instructions per cycle. Instructions per cycle is typically more than one. So nothing lost in talking about IPC, instructions per cycle, as a quantification of performance. Yeah. I think the base assumption is that compilers are all working correctly, right? And yeah, that isn't entirely relevant right now when we talk about analytical modeling. Yeah. That's correct. That's correct. Therefore, whenever I talk about program and input, when I use the word program, I'm referring to an executable file. And if anyone wants to study the same program, I can send them the executable file. And therefore, that will recreate the conditions under which I compiled it. Right? So it's a well-defined unit of work. No, but in this case, the source program is what you started with. Therefore, it's not out of place to think about the source program as being the precursor of the program that I'm talking about here, and that one can be generated from the other by just using the same compiler, right? So this in particular refers to an object program. This refers to an A.O, an executable. So basically the model starts by trying to evaluate something which they call the steady state IPC. Right? So this is some kind of an idealized measure of IPC, instructions per cycle, for that particular program running on that input. And it has a constant value. So it's like the idealization is happening by making certain assumptions about the factors which are actually going to be modeled in addition to the IPC. Let me just put that up. Now, I'll come back to what the idealization is in a second. What the model then does, after computing the steady state IPC of that program running on that input, is to model some first order effects. And it models 3 kinds of first order effects, which will cause the IPC to change during the execution of a program. These 3 first order effects are branch mispredictions, I-cache misses, and data cache misses. So you see that whenever there is any one of these events, the IPC of the program falls, number of instructions which can complete per cycle falls, and then something happens, and then slowly it rises again after the event has been handled, right? So basically the modeling of these 3 kinds of events is the expert knowledge part of this modeling. It is done based on some inside knowledge about how these 3 events are actually handled in the hardware. And that is what leads to these shapes of these of the curves of IPC as each of these events is encountered. So the actual modeling is in the determination of the shape and in capturing its characteristics. Subsequently, all that needs to be done is, in a quick simulation of the program, the number of these events can be counted, and then the CPI for the whole program can be calculated as the steady state CPI plus the sum of the CPIs for each of the events which was modeled, and from that you can get the IPC. This is what they do. And they come up with a situation where their average error is about 6%. For some programs it's higher, 16% and so on. Some programs it's lower. But in general, that's always going to be the case in any of the results that we look at. Therefore, I'll always just refer to the error, and I won't tell you the average error. I won't refer to how it deviates in terms of maximum and minimum. So what is this an error from? Basically, this is an error from the full simulation time for the situation that is being described here. In order to get the parameters for evaluating this model, they use a simulator. And by running the simulator under its full detail of simulation, they come up with an estimate of time and cycles. And therefore, the error that we're referring to here is over a simulator. Right? This is an example of an analytical model. In practice, this is not very useful because it has what is actually a somewhat high error, 5.56%. And further, it requires careful modeling of some events in the lifetime of a program execution. And that is deep expert knowledge. And for minor changes to the architecture, the expert knowledge will change and the equations will all have to change. So all of that will have to be done by experts. Therefore, this is not a generally applicable kind of a modeling technique. Right? Now, there are other kinds of analytical modeling which you could think of. For example, as you may be aware, if you look into a processor, there are a lot of situations where there are queues. Instructions have to wait for events to happen. Therefore, they will be queued somewhere. It could be something which is happening in the processor. It could be something which is happening in the memory. Therefore, you could quite easily build a queuing network model of a processor. Right? It would, of course, be fairly complicated, and you would not be able to use any of the standard solutions for queuing network models, but you would, because you want the whole thing to be program specific. If you can't make assumptions about the properties of the customers arriving at queues and so on, they'll be entirely dependent on the properties of the program which is in question. But you can get some kind of good estimates of waiting times and things like that just using iterative techniques, iterative solution techniques for the queuing network model, such as mean value analysis or things of that kind. So people have tried to do this, but it is laborious, because to get something which is halfway decent in terms of error, you have to model the processor at a very low level, right? A lot of the queues and other queuing mechanisms have to be modeled. So this is not widely done. You won't find any reported literature which uses this approach. However, for subsystems, yeah. Yeah, that's correct. But you'd have to do things for every program and every input that you're going to run through it. And for any change to the processor, you'll have to redo the model. For example, even today, it might not be realistic to just talk about these three delay events. There are a lot of other conditions under which, in order to get a reasonable estimate of IPC, you'll have to take other things into account. And with each development, the number of things you'll have to add is likely to grow. That's one way to look at it, right? So in practice, analytical models may not play a part in this form of work, but they might be good for other reasons. They might be useful, even in the course form of a queuing network model, for giving you a general idea, or for providing motivational examples for use in teaching a computer architecture course. In a computer architecture course, you could reduce a processor to a network of queues, and you could explain why delays here will cause larger delays in the execution of the program and so on. So they have possible pedagogical use, but probably not much use anymore in complex systems. However, if you look into components of a computer, like the memory system, people have been more successful, because one can characterize the stream of accesses going to memory by some statistics relating to that stream. And typically those are enough to come up with some fairly good estimates from which analytical models of performance of memory systems can be adequately estimated. Right? So good for maybe something like a memory system, but not generally good enough for anything else. Right? Which is why the paper that I cited was from 2004. There has been some follow-up work on this, but not with the objective of estimating IPC for a program on an input on a processor. Okay. With that, I'll move on to simulation. And anyone who's taken the architecture course will be aware that the bulk of the evaluation done in computer architecture research is done through simulation. Okay. Now the specific problem which I'll talk about here, just to contain the range of possibilities, is that you don't have access to the hardware and you want to quantitatively evaluate IPC for a program running on a particular input. And you might want to do it for many programs running on many inputs to generate a workload. Because just knowing performance on one program on one input might not be the full story. For example, if you were going through this exercise to decide what computer to buy, you probably want to test it, you probably want to evaluate the performance on 10 or 15 programs that are most important to you. Okay, so what exactly is simulation? As the word suggests, it's something to do with mimicking the behavior of a system, taking into account many of its attributes, but abstracting out a lot of its attributes in order to make the mimicking feasible. Right, so in the case of simulation of computer processors and other components of computer systems, the simulation is done through using a computer program, such as like Gem5. And many of you would have used Gem5. Some of you have also written parts of Gem5. So this is a widely used simulator. Okay. Now, one way to look at what a simulator like Gem5 does is to think of it as being a discrete event simulator. So there are discrete points in time at which the state of the system can change, and in between it is assumed that the state of the system will not change. Right? So this is one way to look at it. It simplifies the construction of the simulator if one makes assumptions of this kind. So basically when the simulation is running, there's a simulation clock which is ticking along as the state of the simulation progresses with the execution of the program. And there could be some relationship between the simulation clock and the processor clock. Therefore, it's possible to think about simulation as happening in a cycle-accurate way. So a simulator like GEM5 might actually be cycle-accurate. In other words, it's taking into account the different activities which could happen in a cycle, but not looking into the activities which happen in portions of a cycle, potentially in great detail, right? So they talk about cycle-accurate simulators. Okay, now the problem with using simulators for real-world work is, in fact, the speed of simulation. If you use a simulator like GEM5, my understanding is this realistic? Yeah. So a few, the speed of GEM5 is capable of simulating programs at a speed of a few 0.1 of MIPS, millions of instructions per second. Millions of instructions per second. So either at 100,000 instructions, say something like 200,000 or 300,000 instructions per second. That's what GEM5 is capable of. And that's not enough. Why? Because you look at your typical spec 2006 CPU program, and it involves the execution of a few trillion instructions. Right? 2 trillion, 3 trillion, 4 trillion. Therefore, to simulate the execution of any one of those programs on any one input would take a few months of CPU time. Right? So this makes it too slow. Therefore, in order to use simulation for a reasonable amount of work, it becomes necessary to speed up the simulators. Right? So, and again, this is something you may have heard about in an architecture course, because it's routine. Everyone has to do this in doing computer architecture research. Okay. Now, one idea that's commonly used in speeding up simulation is to use sampling. The idea here is that instead of doing the simulation through all of simulation time, from the beginning of the execution of the program till the end of the execution of the program, you just select some samples and do the detailed simulation in those intervals of time. For example, the blue intervals of time. And by doing this, you will reduce the simulation time substantially. You could reduce the simulation time substantially. What you're going to do in each of those blue intervals of time is to get an estimate of IPC. Therefore, by doing this throughout the potential execution time of the program, you get a lot of samples, and then you can then aggregate those samples in some way and get an estimate for the IPC of the entire program. And you could think of methodologies for doing this safely, so that you take into account both the initialization and other parts of the program. And one such methodology is what's called systematic sampling, where you periodically take a sample. And this is the idea which is used in this paper from IISc 2003, where they use fixed periodic sampling interval. So periodically they take a sample. The properties of this particular scheme is that they use a small sample size. Each IPC estimate is made on the basis of simulating approximately 1,000 instructions. Right? So you get a lot of samples calculated using IPC simulations of 1,000 cycles, and you aggregate them. Okay, now, and further, this technique has the advantage that it expects you to specify how many samples are enough. As soon as some specified error criterion has been met, the error being no more than a certain value, the simulation can actually be stopped. Right? Therefore, one doesn't have to keep on simulating until the end of the program, but could potentially stop before that. All right. So the bottom line, let me just explain what this involves. So this is extracted from the IISc 2003 paper. So what's shown there is the simulation timeline discretized to units of time that are sample intervals. So I'm sorry, this is not time, but this is a count of the number of instructions. I'm sorry. So this is discretized in terms of thousands of instructions. And periodically a sample is taken. You can see the period over there. 1,000 instructions are simulated in detail. Now, in computer architecture, this will actually cause some of these later samples to become extreme. The first sample might be extremely accurate. So the sample that you take many unsimulated cycles later is not going to be very accurate, because the simulator would not have updated the state of the various instructions that are executed between those black intervals. And therefore, the state of the simulator will be inaccurate. And therefore, the quality of the sample estimate of IPC will be very poor. Therefore, in order to make this idea work, you actually have to do what is called warming up. Before each sample is generated, you'll actually have to do some simulation where you do almost as much work as you did while you were simulating the simulator will have to be updating the state so that the quality of the sample when it is estimated will be as good as possible. But in order to do this, it's actually necessary to do a little bit of work right through the execution run, the simulation run. Right? So the way that you look at it is, there are certain large structures in the simulator, large state structures, which if you don't actually keep them updated all the time, then you just try to update them for short intervals of time, like this warm-up period over here, then they might not become realistic enough to produce a good estimate. Therefore, those large structures might have to be warmed up right through the experiment, the measurement experiment. So the bottom line is, even if you take a small number of samples, you might have to do a reasonable amount of work, but not as much work as you'd have to do if you were doing the simulation in black of the whole execution. Right? So they get an average speed up of about 30. An average speed up of about 30 over running the simulation in detail from beginning till end. So that's a substantial speed up. What does this mean? This means that in order to simulate one of the spec programs, it wouldn't take several months, but it would take only several days, right? Which is more acceptable, right? Again, each of you has a target. If you're working in computer architecture and you have a target of graduating in 5 years, and you know that you have to do 5,000 experiments, this gives you some hope. Well, maybe not, but okay. Further, the error is not as high as it was in the case of the analytical model, which is not surprising, right? Yeah, but the user can't specify something which is not achievable with this methodology. Again, one could actually give that kind of an error estimate by simulating throughout, right? By making the period of simulation small and by increasing the sample size. But under the parameters that they're playing with, where they want to get speed up of at least an order of magnitude, they could get no better than 2% error. Yeah. No, it's not a question of the application. It's a question of what your objective in getting these. Let's be pragmatic about it. For an IISc paper to get accepted, you need to have a speed up of at least 5%. If in generating these results you had simulation errors of 6% because of the methodology that you're using, you should hope that the referees would notice this and would just reject the paper outright, right? So it does matter sometimes, which is. I think Arka will have to answer that question. Yeah. Okay. So moving right ahead, I'll talk about one other use of sampling. So instead of doing this periodic sampling, another idea from the early parts of the century were to use pre-computed sampling points. Right? And Typically in this kind of an approach, the sample size is going to be very large because the number of samples that's going to be taken is small, and therefore the sample size has to be large enough so that the warming up happens within the sample itself. So 100 million instructions is not unusual for samples which are using pre-computed sample points like the one which I'm talking about here. Now the scheme which is described in ASPLOS 2002 is a scheme called SimPoint. So it gives you pre-computed simulation points. What does that mean? That means that if you looked into the literature, you will find a table which for each program and each input will tell you exactly what your simulation point is. For example, if I was interested in the program called APSI, which is, the table contains only one input for that, it tells me that the simulation point that I need to use is 3409. And therefore, all that I have to do is to simulate 100 million instructions at that point in the simulation. So I can fast forward the simulation until that point using functional simulation or something. As soon as I reach that PC value, I can simulate 100 million instructions, and that will be a good estimate of IPC. Right? How do they come up with this? They come up with this by a lot of work offline before, in order to generate this table, right? Which will involve somehow figuring out which of the 100 million instruction windows in the execution of this program is most representative of the entire execution of the program. Right? In some cases, it may not be possible to isolate onto one point, in which case, for which purpose they give you also the option of using multiple simulation points, where you can simulate, for example, over here they show you multiple simulation points, and the weight that you should give for the sample coming from each of those simulation points, so that you can combine them into an estimate of IPC. But the total amount of work that's done is going to be much less than simulating the entire program, even though you're simulating hundreds of millions of instructions. So this gives a speed up over SMARTS, the previous scheme, by about a factor of 2, right? With a slight increase in error. Yeah? Yeah. All of this is for single-threaded, single core execution. But many of these ideas, attempts have been made to extend many of these ideas to multi-cores, right? Okay, so this is one idea. You can speed up simulation by using sampling. Another idea is you can speed up simulation through parallelism, right? You can somehow exploit parallelism. And one idea you might think of is, instead of setting up the simulator so that it does discrete event simulation, you can set it up so that it's actually exploits parallelism within the simulation. Right? So if it's possible to identify different event handlers which are independent of each other, then, for example, if you could partition all the event handlers into two groups which are completely independent in terms of their updating of state, system state, you can actually execute them in parallel. Okay, so in practice, this doesn't help a lot in case of simulator like, for example, GEM5. You might be able to get a little bit of parallelism, but not enough, not an order of magnitude parallelism. Is there any parallelism exploited in GEM5? Yeah. Yeah. And the best way to understand why is that you want to think about it as discrete event simulation, and that to get two activities which can run in parallel 100%, you actually have to partition the events, and therefore there'd have to be a partition of the state space, which is unlikely to be significant in the state of a processor, because there are these central points where the central points which are there. Okay. The other thing which you can obviously do is you can speed things up by executing independent simulation runs in parallel. So your 5-year target for the PhD or the MTech research can be reached by, instead of running everything on your laptop, you run it on 10 servers in CSA plus 10 servers in SERC, and then suddenly, instead of 5 years, you'll get it done in a couple of months. Parallelism. That's obvious. Now, something which is not as obvious is that you could, if you use a sampling kind of an approach, it's actually possible to simulate samples in parallel. For example, if you're talking about SimPoint, if you're talking about the SMARTS idea where I'm doing a lot of samples, if I could simulate all of those samples in parallel, and there were, let's say, 500 samples, if I could simulate all of them in parallel, then the effect would be that the amount of time would come down by a factor of 500, right? Okay. Yeah, so we'd have to worry about the state. So the question is, how can this be done? Now, this is something which was done in a paper published in HPCA 2016, which at least two of you know something about. Right? The rest of you may not have come across this. So what's the idea here? The idea here is that you're, just like in the case of SimPoint, where you did a lot of work offline, here you're going to do a lot of work every time you want to run a simulation as a setup element. So what they do in the setup is they create periodic functional mode in-memory checkpoints. In other words, they run a functional simulator on the whole execution of the program. A functional simulator is not keeping track of much processor state, if any. Right? It's just keeping track of the program state. Periodically, they dump a checkpoint. Right? So a checkpoint is something from which you can resume the simulation from that point in time. Therefore, the state of the program will be available at each of the checkpoints, any of the dumped checkpoints. These are in memory, so you'll need a lot of memory to use this scheme. If you want to have 1,000 checkpoints, you'll have each of these checkpoints might be 20 megabytes in size. So you need a lot of memory to do this. But if you have a lot of memory, then you could go ahead and you could calibrate. After getting all the checkpoints, they have a state called calibration, where they simulate each using a microarchitecture simulator, which is loaded as a dynamic library. So they actually run each of the samples through a microarchitecture simulator to come up with some kind of a performance estimate for that sample. And then they cluster those samples to find out which are the samples which are different from each other. Subsequently, they will concentrate on those samples which must be simulated and no others. So they get some of the benefits that come from the pre-processing of SimPoint by doing the clustering in the previous step. And in fact, they can do this fast enough that they can actually aim towards a real-time guarantee. Right? They'll simulate enough checkpoints to finish the entire simulation in some amount of time that you specify. If you say 5 seconds, they'll do it in 5 seconds. If you tell them that you have 10 seconds to wait for the simulation, they'll do it in 10 seconds. Right? So within reason, it can't be shrunk much further than that. So the bottom line is that this is a situation where the simulator is going to run at a speed up from the actual execution time of the program. The simulation is going to run faster than the program would run on the actual hardware. So we don't talk about slowdown, we talk about speed up. So this is, in essence, this is combining both of the ideas that we saw along with some other paraphernalia. Yeah? Yeah, they're all deterministic. Why? Yeah, yeah, that's correct. So this won't work for all programs, right? So back to that question, there's a little bit of additional work which will have to be done, and a little bit of additional state which will have to be included in the checkpoints relating to the warm up of things like the large hardware structures, because they do still have to be kept warmed up at the point in time that the simulation is done. So there's a little bit of technical stuff which I'm not getting into here at all. And that is part of the reason that the checkpoint size might be a little larger than you expect. Okay, moving right ahead. With that, I said very little about analytical and a little bit about simulation. I'm going to talk very little about empirical modeling as well, not too much. So as I said, the basic idea in empirical modeling is that the model building is based on observations or experiments. So you're going to get data out of experiments and you're going to use that to build the model. And a situation where this might be useful is in a situation where you have to use design space exploration, such as the one which I mentioned as the second objective in one of the early slides, where you want to identify the best microarchitecture configuration for a given program input. I use the example of the washing machine, right? So for that kind of a design space exploration, it might help to have a model of this kind. simulation could be used. I'm not talking about using live sim, but simulation could, the other simulation speed up techniques could be used, but they would still be too slow. And therefore, one might want to end up building an empirically built model. Right? Basically, this is just an example of using machine learning. The idea is that if you have a simulator which is reasonably good, you can use it to generate a lot of data about the behavior of the program and that input for different points in the design space. Right? So you pick a large number of points in the design space and you simulate them and you get data. Then you just build a model, you train a model, your favorite machine learning model, and then you use a trained model to predict performance at any desired microarchitecture configuration. So using that model, you can quickly step through the design space and pick the optimal point. Right? So this is the idea which is used in some work. This has become somewhat popular in the last 10, 12 years or so. And as I said, it's widely used in embedded computing scenarios. Right? So in this particular case, the sampling of the design space is done using I believe it is A-optimal experimental designs. So there's a need to have enough representation from different parts of the design space. Otherwise, this technique is not guaranteed to be good enough for design space exploration. So the nature of the sampling of the design space in picking the points at which the data is going to be generated must be done carefully. Further, yeah, that's okay. Then what is done in this piece of work is to use a stepwise model building technique. So it starts off by building a model which has one term, right? Then it adds another term, but it also looks at interactions between microarchitecture factors, right? So there could be a square term, there could be a x squared multiplied by y term in this model that's being built up, right? Interactions between factors. The net effect is that it's possible to build models which have error which is comparable to the error generated by the simulator which was used to generate the data on the 2% error type situation. Right? So increasingly this is being used in certain settings. There's also an attempt to use this kind of technique for other kinds of evaluation objectives, such as given a program and an input, if you want to figure out whether to run the program on a multi-core CPU or on a single CPU which has a GPU attached to it. So building models for this kind of a situation, for selection of platform type, are also being attempted through this kind of empirical modeling. Because in those situations too, it is possible to generate enough data for a model to be built. In this particular paper, the number of data points which were needed to generate the model was about 300 to 400 for each program input pair. It's not a small amount of data that is used. A fairly substantial amount of data might have to be used. Yeah, yeah. So I think that has been attempted also since 2006. So each of these pieces of work that I mentioned, other than the 2016, there is some forward progress which has been made and the techniques have been improved. Okay. Now just to wind back to the beginning of the talk, I said that there were two evaluation options. One was modeling, which I've talked about for some time. And now I'm not going to talk about measurement very little. And I'm going to talk about measurement in a specific evaluation objective, which is not either of the evaluation objectives that you see here, but a new one. So the new evaluation objective is, what are the architectural bottlenecks in the execution of this program input? So you have a program and an input, and you want to figure out what are the bottlenecks within the architecture, microarchitectural bottlenecks as far as the execution of this program are concerned. Okay, now if you look back to, if you think back to the early slide where we talked about Karkanis and Smith's analytical model for superscalar processor IPC or CPI, you remember that fundamentally what they were doing was coming up with some way to model the steady state IPC in the absence of several of these factors like branch mispredictions, cache misses, and so on, TLB misses, and so on, and subsequently add to the CPI a new term. In other words, in effect, what they were doing is they were looking at the CPI of the program and estimating different components of the CPI. And by estimating the components of the CPI, there was CPI TLB missed, CPI branch prediction missed, and so on, branch misprediction. So in essence, what they were doing is something like this. They were analyzing data, but what they were doing was they were coming up with an estimate of CPI as a sum of CPIs due to various causes. The effect was the CPI got increased. So for example, in this particular CPI breakup, which was for 2LF on some input, you notice that the baseline CPI is only about 0.3. This is a 2006 paper. But the overall CPI cycles per instruction was as much as almost 1.4, right? And by looking at this, you look at that large pink, whatever, maroon, whatever this color is, L2 decache, and you suspect that something here which is largely due to the L2 decache, right? So in some sense, by looking at this kind of CPI stack, microarchitectural bottlenecks seem to be highlighted. Right? That's one reason that one looks at that kind of a CPU stack. Okay, so the question which arises is, if CPU stacks are useful, maybe it's possible to measure CPU stacks. Instead of having to do simulation to gather CPU stacks for programs and inputs, maybe you can measure the CPU stack components for a program and an input. Right? And that is basically what this piece of work does. Ironman et al., a performance counter architecture for computing accurate CPI components, as per 2006. And what this paper essentially does is, it applies the interval analysis of Karkanis and Smith. If you think about what Karkanis and Smith is doing, they are looking at the execution time of a program as intervals, each of which ends with one of these miss events. So there's some time of being in the steady state IPC, and then there's a miss event which causes the IPC to drop. So they view the lifetime of the program execution as being made up of such intervals. So that's referred to as interval analysis. So by using something similar to what Karkanis and Smith did, by adding to the intervals, the nature of the intervals that are under analysis, and for each interval they identify what hardware performance counter events may be necessary, they are able to cause these to be built into the processor, and then the CPI stack can be generated during the execution of the program. We're just enabling the appropriate performance counter events, right? So with this picture of the CPI stack, the question that comes next is, you want to be able to do this for program bottlenecks in general, not just for aspects that we could easily understand as in terms of the microarchitecture. So the objective of this slide is to talk about another piece of work which is trying to assist programmers in identifying program bottlenecks in general. It's not just trying to highlight problems with the memory system, but a wider variety of program bottlenecks. And this was an IISc's 2014 paper, essentially out of Intel, which designed the technique called top-down design, top-down method for performance analysis and counters architecture. And once again, this is basically just extending interval analysis into a hierarchy of bottleneck causes, and then identifies required performance counter events through which the programmer can then do a dive down the hierarchy to isolate onto a particular bottleneck. So this is the hierarchy that is proposed in that paper. At the top of the hierarchy, you have events which are going to be able to figure out if the bottleneck is at the front end of the processor or the back end of the processor, or predominantly due to bad speculation or due to retiring. And as soon as one of these is identified as a bottleneck, the programmer can then do a run in which he looks at the next level and enables the event counters for the next lower level in the hierarchy in order to isolate onto some particular nature of bottleneck, which might be something that can be understood in the light of the program, which the program can be modified to handle the bottleneck, right? So this essentially derives out of Karkanis and Smith's model, interval analysis, and actually gives some direction for the design of performance counters, which might be practically useful to both the programmer and to the microarchitect. So it leads into the whole idea of performance counter event design. Okay. Right. So with this, we've looked at modeling and measurement. I looked at a few examples of techniques in each. And that's all that I was going to talk about.